So basics of functions. Don't write that yet. We're about to switch screens. Oh, sorry about that. Now let's go. All right, so looking at our functions, we're starting off with the definition of a relation. A relation is any set of ordered pairs. So in this example, we have 1, 2, 3, 4, 5, 6. So we have 3 ordered pairs here. And this is going to be an example of a relation. And the domain is the set of all of the first components of the ordered pairs. So in this case, 1, 3, 5.
Professor Tucker?
Yes.
This is the beginning part. I just joined a little late, sorry.
Yeah, this is it.
This is the first definition, right?
Uh-huh.
Okay.
The title was basics of functions.
The basis of function?
Mm-hmm. 2.1. Can I scroll up? Of course, let me know if I scroll up too quick.
Yeah, just hold on right there.
Okay, right there.
Sorry, I'm just running a little late.
Yeah, let me know when you're done, when you caught up.
Yes, sir. Professor Tucker, I'm all caught up.
Sounds good.
Thank you.
Good. Not a problem. So we're looking at the range now. Remember, domain is a set of all of your first components of the order pairs. Range is the set of all of your second components of your order pairs. So in this case, we would have 2, 4, and 6. That would be your range. And we should be done with domain, right? All right. So after we finish writing down the range, we'll look at direct comparisons between the two, domain and range. All right, so domain and range direct comparison. We already mentioned that your domain is your first component, range is the second component. That means your domain will be your x variables when your range will be your y variables. Your domain is also your input, range is your output. Domain is your independent variable, range is your dependent variable. and also your horizontal axis versus your vertical axis. All right. All right, so definition of a function. A function is a relation in which the elements from the domain corresponds to exactly one element in the range. All right. So first example under this is to determine whether each relation is a function. So in this example, once again, we determine whether each relation is a function. Next one, notice the difference. We'll be trying to determine whether each equation is a function. So, right, erase this real quick. Scroll back down. Okay, wait for you guys to write that, then we'll look at it. All right, so I would do a mini mapping of what our domain going to our range will look like. Here we have our domain. Domain is 1, 2, 3, 4. Our range is 6, 8, and 9. So we don't have to write 6 twice. You know, it's already there once. That's good enough. So now what you're going to ask is, remember, to be a function, each element in your domain has to go to one value in your range, or one element in your range. So you look at each domain value individually and ask the question, is it going to just one value? So is 1 going to just one value? The answer is yes. Is 2 going to one value? The answer is yes. Even though it's going to the same one that 1 went to, it's still only going to one value. Is 3 going to one value? The answer is yes. And 4, the answer is yes as well. So each one of those values are going to one value in the range. So that's why it is a function. Okay. So of course I'll show you one in which it would not be a function, how that would look, and you'll see a clear distinction. But questions on this, you want to look at each one of your values in the domain individually. Ask, is it going to one value in the range? And if that answer is yes for each one, then we're in a good place. That's a function.
So you're saying it doesn't matter as long as it goes into one of them?
Yep. As long as it only goes to one value in the range. As long as it only goes to one value in the range. All right, so the next one, 6162 8394. So when I look at my domain is 689. Range is 1, 2, 3, 4. So once again, you're going to ask yourself, is each value in the domain going to go to just one value in the range? So when you look at 6, 6 is going to go to 1, but then it's also going to go to 2. So no, it does not go to just one value in the range. So that means it is not a function. All right, questions before I scroll up? All right. So just a couple of statements about what we just saw. First one, there can be a repeated value in the range, but no value can repeat in the domain. So real quick, what we mean by that is when it was a function, we had a 6 that was repeated in the range. When it wasn't a function, we had a 6 that was repeated in the domain. So just a general statement, there can be a repeated value in the range, but no value can repeat in the domain if you want it to be a function. And then the next statement, the range can go to more than one value, domain can only go to one value. There's other ways of looking at how you can determine whether you have a function or not. All right. Are we good to go? Can I leave this page? Anybody holding on to it? All right. So now we're picking up here. And like I said, this was my notes, the go to functions in 154. That was for me. So now we're here. Determine whether each is an equation or whether each is an equation that defines y as a function of x. So before we had a relation and we're trying to see if that was a function. Now we have equations that we're going to look at to see if we can tell if they're a function or not. All right. So this is our first equation. X squared plus y equal to 4. And if we want to see if the equation defines y as a function of x, the first thing we have to do is solve it for y. All right, so solving for y, we subtract x squared from both sides. That'll give us y equal to 4 minus x squared. And step 2, we want to evaluate to see if multiple y values can be produced. And that'll be easier seen when we look at the next example, what we mean by that. But you want to see if multiple y values will be produced when you plug in an x value. Remember, you cannot have a value from your domain going to multiple values in your range. So in other words, you cannot have an x value produce multiple y values. And so that's what we're going to look for. Now in this scenario, it's going to be a function because no matter what I plug in for x, I'm only going to get one value. So if I plug in +1, I will get 3. Plug in -1, you get 3. Plug in 2, you get 0. Just plug in a few points just to prove that each x value will produce just one y value.
Professor Tucker,
Yes, sir.
I could be thinking too hard.
Uh-huh.
I see a difference of squares.
Yes.
So I can do a plus b, a minus b.
You could have. Now, that's if you were trying to solve it. We're not trying to solve it, though.
Okay.
Yeah, we're not trying to solve. We're just trying to prove or see if this is a function or not.
Okay.
Mm-hmm.
I'm reading and reacting.
Yeah.
Football.
So if it says solve, then that would be the move to make. Like if you're trying to solve this. But now also recognize you have two unknowns here. So you would need more information in order to solve for both variables.
All right. Thank you.
Yep, not a problem. Saw somebody said something in the notes. So basically it has to be more domains than ranges. You'll see in a second what I mean by producing more than one value. Let me show you one that's going to not be a function, and it would be more evident what I mean by that. So let's look at the next one, and then if you still have a question, let's explore that. All right. So this is a function because no matter what I plug in for x, I will only get one value, one y value. All right. So wait for you guys to finish copying before we go to the next one. There's going to be something that's key that you'll look for, and then something that will not be a function, and help us distinguish between the two.
What's this statement written in red at the top? Can you scroll up a little?
You don't. All right. Yeah, are we good to go? Somebody else said something in the chat. Somebody asked where did I get 1, -1, and 2. I chose that. So you can choose any values. Remember, whenever you're trying to test your equations, you can choose whatever values you want to test your equation. Not a problem. All right. And so it's always good to choose a value and then the negative of that value to see if they, create anything different, So that's why I chose 1 and -1. I just chose 2 just to, just as another point. But yeah. All right, is everybody good with this first one before we go to the next one? No, y could have been anything. Y just so happened to be 0 because when you plug 2 into the equation here, you got 0 out. So I chose these 3, 1, -1, and 2. And then I got out those 3 because of the equation that we had. So 3, 3, and 0 just so happen to be what they are because I chose, I plug in 1, got out 3, plug in -1, got out 3, plug in 2, got 0. I could have chose 5 and then I would get another number out. So I just chose those values to see. See, the main thing you want to see was are you going to produce more than one y value? And like I said, when we look at the next one, you'll see what I mean by that. Somebody else said something in chat. Yep, any number you want. Because all you're trying to do is test your equation to see, are you going to get more than one y value? All right. All right, so let's look at the next one. So what's going to be key in the next one is the fact that we have an even power on the y value. Because remember, our first move is to solve for y. If we want to see if a function is, if y is a function of x, you solve it for y. And if you have this even power on y, remember the square root property. Whenever you take the square root of both sides, it's going to give you this plus or minus. All right. So that even power on the y, whether it's 4 power, 6 power, talking about the even power on the y, will produce this result here. All right. So before we evaluate it, questions on what happened. We solve for y, so we subtract the x squared from both sides. Then we have to take the square root to get that square off of y. And that gives us plus or minus square root of 4 minus x squared. And once again, that plus or minus occurred because we had to take the square root. And that square root, taking the square root of both sides, produces that plus or minus. So now I'm going to choose positive 1 to plug in. Once again, I chose that. You could have chosen anything, but the result is still going to be the same. And what I mean by that is that when I plug in positive 1, I get negative square root of 3 and positive square root of 3 as an answer or answers. In other words, when I plug in one number, I get out 2 numbers. So if I were to do a mapping, that 1 would go to square root of 3 and it would go to negative square root of 3. And remember, that's what stopped our relation from being a function. When you have a number in your domain going to more than one value in your range. And once again, this scenario was created because you had a even power on your y. And so in the blue is our conclusion that x produced 2 y values. So this is not a function. And notice I didn't put that the 1 produced 2 y values because any x you plug in will produce more than 1 y value. And so that's what will make it not a function.
So it's a function when it only produces one value, right?
Yes.
When domain is equal to just one range, like, you get what I'm saying?
Mm-hmm. Yeah.
Yeah,
Yep.
like
Wait.
when one variable domain is equal to one variable of range.
Mm-hmm. That's exactly what it is. Yep.
So it's not a function when one domain is equal to 2 ranges, but 2 range or multiple more other ranges can be equal to one domain. That's still
Right.
a function.
Right. That's still a function. It's all right. For a function is based on the domain's relationship with the range.
Mm-hmm.
And so you're talking about your domain going to just one value in your range. That would be the function. Yep.
I got you.
Mm-hmm.
Thank you.
Professor Tucker,
Not a problem. Yes, sir.
x just disappears
When?
when you go to the square root of 4 minus x squared
Right here?
above it.
Right here?
Yes.
What you mean x disappears?
I notice
So,
it, you turn it into a 1.
well, x is going to disappear when you plug in 1 for x. If that's, are you talking about that? Not sure what you mean by x disappearing because, Say again.
I'm trying to figure out how the x just turns into 1.
Oh, I chose X. Remember what we're doing is testing your equation.
Okay.
Showing algebraic proof as to why, because we used to have a thing. I don't know if they make you do. Well, you can't make you do it in my math lab necessarily, but when back in the day when we used to write down stuff all the time and had to turn in assignments, and they had nothing to do with the computer, right? We had to actually show algebraic proof as to why our function isn't, or why our equation is not a function. So this would be an algebraic proof. You would choose an X value, and that X value would produce two Y values. So
Okay.
yeah, so that's all this is testing your equation, and that's your algebraic proof that is not a function.
You take your numbers from your domain and plug it into your x.
Yes,
Okay.
yes.
Sorry.
No, you're fine. You're fine. Get the clarity, get the clarity. But yeah, man, back in the day when we used to chisel all of our math into tablet stones and stuff, you had to actually turn in assignments. So yeah. Any questions before we scroll up? Look at the vertical line test. When we look at the vertical line test, that's why I said this is your proof algebraically, because you can also prove it graphically. You could throw this equation in graphing tool and then perform the vertical line test. And the vertical line test, it says that any vertical line crosses or touches your graph more than once, then it's not a function. So, it eliminates the need for the algebraic proof. But, like I said, still should be able to show it if asked. All right, so if I had a circle, that's not a function, because if I draw a line through it, it's going to touch twice. If I had my linear equation that produces a line, no matter where I draw the line, it touches it once. Then here, parabola only touches it once, no matter where you draw your vertical line. So the answer is yes, it is a function. Then this diagram, this graph down here, even though it only touches it once, in the tail, when you get to this part right here, it touches it 3 times. So it's still not a function. So if a vertical line crosses or touches your graph more than once, it is not a function, not a function. All right, questions on the vertical line test? All right, scrolling up. Function notation. Y is equal to f of x. And that's how we say that, f of x. So from this point forward, y and f of x are interchangeable. They could change that up within the problem. In other words, substitute one for the other and vice versa. And they expect you to know that f of x and y are the same thing. It's just that f of x, oh, didn't change that off. There we go. F of x equal to 2x plus 1 is actually in function notation. So that's considered function notation when you have that f parentheses x, or g parentheses t, s parentheses r. You can use whatever set of letters, but that's considered your function notation. So the purpose of function notation is to give you instructions without actually having to write out a sentence. So let's say if it said find f of 3. Well, even if they didn't say find f of 3, if you wanted to know what f of 3 was, then you know that you need to take 3 and plug it into this function. All right. Notice in the notation you had f of x, but then you substitute 3 in for the x. That means you would substitute 3 in for the x throughout that function. And so that means you would do 2 times 3 plus 1, because we had 2 times x plus 1. 2 times 3 is 6. 6 plus 1 is 7. So f of 3 is equal to 7. Also, if you see f of 3 is equal to 7, that lets us know that this is our ordered pair, 3, 7. All right. Questions on that? Anything that was said before we do an example of that? So all you're doing is taking the number that's in the parentheses, plugging it into the function, and calculating and simplifying. Yep. All right, can I scroll up? All right, so the next one, we have f of x is equal to x squared plus 3x plus 5. That 3 just said, that was just where they, if they told you, if the direction said find f of 3. So if those are the directions, then you just plug it in. Just like in this next one, we have f of x is equal to x squared plus 3x plus 5. It says find, and in this case, f of 2. So you just plug in 2 into your equation, into your function. All right. And so that's what we did right there. F of 2 is 2 squared plus 3 times 2 plus 5. 2 squared is 4. 3 times 2 is 6. 4 plus 6 plus 5 is 15. All right. Next one, we want to plug in x plus 3, where we see x in both cases here. So that's what it looks like. So we have f of x plus 3 is going to be x plus 3 squared plus x 3 times x plus 3 plus 5. So be careful here. You cannot just square x and square 3. You have to expand that out, and that's what we did over here. That's x plus 3 times x plus 3, and then you FOIL out. That'll be x squared plus 3x plus 3x plus 9. And then that will give you this expression once you combine your like terms. X squared plus 6x plus 9. All right. Let me erase this. Then distribute that 3 there. That'll be 3x plus 9, and that'll be this expression. And then you see in the back you have plus 5. So from there, combine your like terms. X squared couldn't be added to anything, so you just bring it down. Then you have 6x and 3x, which is 9x. 9 plus 9 plus 5 is 23. All right, any questions before we do a little bit out of 2-2? That was it for 2-1. And we're gonna do some of the stuff out of 2, 2. All right. All right, so 2.2 is more on functions. A function is increasing on an open interval when your x value is increasing, the y value is increasing. So in other words, you're going from left to right. You're always reading it from left to right. And as you go from left to right, your y is increasing. In other words, your graph is going up. So that's why you have that red arrow following it up. Once again, you always read it from left to right. Decreasing, once again, you're reading from left to right. But as x increases, your y decreases. So you'll be going down as you read it from left to right. All right. And then constant on that open interval as the x value increases. And once again, that means as we go from left to right, your y value stays the same. In other words, it stays constant. So that gives you a horizontal line. All right, and everybody okay? All right, anybody still copying the constant? All right, so this first one, state the intervals on which each is increasing, decreasing, or constant. So if you copy, see something real quick. All right, so we look at what we have here. Notice when you're setting up your intervals, you will always use the x values because we're reading it from left to right. We're going from left to right. So we're always using our x values to set up our intervals. So coming from negative infinity, notice it is going up. So that means we're increasing. And we're increasing up to here, which is -2. So that's what we have here from negative infinity to -2 for increasing. Then we're going to be constant from -2 to +2. And so that's what we have right here. And then from +2 to positive infinity, we are going down. And so it's decreasing to the positive infinity. Notice we use parentheses on all of our intervals because it's an open interval. Remember we said it was open interval. So you will use parentheses on all of these. All right. Questions on that before we look at B? So it's increasing, it's going up when you move from left to right. Decreasing is going down as you move from left to right. And then constant is staying the same or level as you move from left to right. All right. Next example, very similar. So coming from negative infinity, right here we have to 0 because that's our origin. We are going down. So that's why we have negative infinity to 0 as our decreasing. Then from 0 to this point right here, which is 2, is increasing. And that's what we have right here. 0, 2 is going up. And then from that 2 to positive infinity, remember we talked about going all the way to the right to infinity, it's going down again. So that's where we have this part right here. So it's actually decreasing on 2 intervals and increasing in that middle part, the middle slot. And then there's no constant in this relationship, no constant in this graph, no constant interval. All right, questions, any questions?
Just a quick question, Professor Tucker.
Yep.
For the decreasing part, I always get confused at the second one, not the first one where it's from negative infinity to 0, but where it's saying 2 to infinity. So are we looking at the 2 that's the y value 2 or the x value 2? Because I know it's supposed to be x, but here they both have 2, so that kind of confuses me sometimes.
Right. And what I probably should have done just to make that distinction is just probably threw another one in there like that, just so they wouldn't be the same. Because I had no one haven't even messed with it, or asked me that question before now.
So that's the x value 2. That's the x2 over here,
it's
right?
always
Because x always first and y second.
Well, we're doing this because we're reading our intervals or our graph behavior from left to right.
Yeah.
See, if we were going up and down, then we would be dependent on our y. But we're looking at the behavior from left to right, and that's why we're dependent on our x.
Are we going to talk about the other one where it's no? Okay, so
they're always discussed going from left to right.
Okay. Thank you, Professor Tucker.
Not a problem. Good question. All right. Anything else before we go to our extremes? All right. So relative extrema, just a relative max. It's going to be the maximum value relative to an open interval, or the relative minimum would be the minimum value relative to an open interval. So you're just talking about the largest value and the smallest value in an interval. That's all that means. Because sometimes you don't have an extreme or a large value or smallest value in a graph or in a function. For example, if you look at this one right here, this goes on to infinity, to positive infinity. This goes on to negative infinity. So there's never really a largest value and a smallest value because it's always going to go up. So you would look at something like this and say that this will be my relative max, because it's the largest value at a certain interval, like in between those two lines. And then this would be my relative minimum, because that would be my smallest value within those two lines, or whatever our intervals are. So if I were to set up these two intervals, this would be my largest value, this would be my smallest value. I mean, whatever your interval you're trying to examine and what you are examining depends on what the application is. So you will get more into that as far as calculus is concerned. What pieces you're looking at versus what pieces you're not looking at. But when you talk about relative max versus a relative minimum, what is the largest value in that interval? What is the smallest value in that interval? Because like I said, when you look at a parabola, this is your maximum. It's not a relative max or relative min. That is your maximum because no value gets higher than the vertex. Same thing here with the other side of it. No value gets lower than the vertex. So that is your minimum. But you don't have to worry about a relative minimum because that is the smallest value. But like I said, here you don't have that because these values go, or this equation will take you to positive infinity and negative infinity. So that's why you would look for relative maximums and relative minimums. So, yep. And that's all based on whatever your interval is when you're doing your, whether it be research or application.
Is that what makes it an open interval? Like the line just continues like to infinity at a certain point?
Well,
The closed interval, would it be like two numbers where it stops at a certain point?
right. Well, now closed interval versus an open interval. So when you use parentheses, you're saying that it's open. That means, let's say if it goes from 2 to 3, I cannot use 2 and 3 as a part of whatever it is I'm analyzing.
Mm-hmm.
But when it's closed, that means I can use 2 or 3 as a part of, like if it's my solution or whatever. So that's why I would use brackets.
Oh, okay.
Yeah, so I can get as close to 2 and 3 as I want here, but I cannot use 2 and 3. And then here, I can use 2 and 3. So when we go back to our intervals, you know, at this point, it's not increasing or decreasing, it's just a point. So I can't use 2, in this case 2, as a part of it's increasing or decreasing, because it's not increasing at that point, it's just there as an apex. And then when you go down, that's when the interval starts. And so that's why they're open intervals. Yeah. All right, good questions, good question. Everybody good before we look at symmetry? All right, so let's look at the definition of symmetry. Symmetric with respect to the y-axis. So for every point on the graph, the point negative x and y is also on the graph. So the way we would test this symmetry is by substituting negative x in for x. And then if the result is the original equation, then it is symmetric with respect to y. All right, symmetric with respect to the x-axis. For every point on the graph, the point x negative y is also on the graph. So that test will plug in negative y for y. And if it results in the original equation, then that means it is symmetric with respect to the x-axis. All right. And then the third one, symmetric with respect to the origin. For every point on the graph, for every point on the graph, the point negative x, negative y is also on the graph.
Could you scroll up just a little bit? I missed the symmetry with respect to the
X-axis? Oh,
X.
yeah.
Let's get that one.
Okay. So, symmetric with respect to the origin. So for every point on the graph, the point negative x, negative y is also on the graph. And we'll look at the test for symmetry on that one in a second. we done with that black up there. Okay. All right, so the test for symmetry with respect to the origin, you'll plug in negative x for x, plug in negative y for y, and then if it results in the original equation, then that means it is symmetric with respect to the origin. All right. Good, I'm scrolling up. Is that okay? Okay. So for this example, it emphasizes that you want to determine whether the graph of x equal to y squared minus 1 is symmetric to the y-axis, the x-axis, or the origin. Doesn't matter which one you decide you do first or which one you decide to find first. There are 3 individual tests. So if I want to know if my graph or if my function is symmetric to the y-axis, the first thing I would do is substitute in negative x for x. So my equation was x equal to y squared minus 1. Plug in negative x for x, and that'll give me this right here, which is negative x equal to y squared minus 1. So now I want to make a clean comparison to what I have, my original equation, which is x equal to y squared minus 1. So I'm going to multiply both sides by negative 1. Multiply each term by negative 1. Let's see. Okay, so I just saw that people asked about the y-axis part. Did you guys get it? Because I didn't see that until just now.
I, I, I don't understand this part. Like you said, substitute negative x for x, but the equation says it's a positive x. So if it's a positive, then we substitute negative x.
Well, it's always going to be, the equation is going to be whatever it is. But
Okay.
you're always going to plug in a negative x to see if you're going to get if the result that you have, excuse me, if the result that you have and everything's said and done, if it's the exact same thing
As that.
as that, once you're done simplifying and everything, then that lets us know we have symmetry.
And where'd you get this -1 from over here in the red?
Right, that's what I was trying to explain. But I saw some people, I saw some people in the chat had requested, I think it was about 4 minutes ago, about the y-axis part. Let me finish this explanation, then I'll double back to see if anybody needs that. So what I was saying is that, okay, the first thing that you do is you plug in negative x for x. All right. And so to make a clean comparison to what I have right here, I have x equal to y squared minus 1. I'm going to multiply this -1 to both sides so I can say x equals 2 and make a clean comparison to what I had originally. So I multiply both sides by -1. So now I have x equal to negative y squared plus 1. Hold on 1 second. My apologies.
Very good. So the
So,
-1 is the negative x over here, right?
yeah, right here.
Yeah, that -1
Mm-hmm.
is that substitute negative x, right?
All right. So I substituted negative x right here for
Okay,
this x.
okay.
So now I want to make a clear comparison to this equation, but I
Mhm.
have negative right now. I have this.
Yeah, right now you have a negative x equals y squared minus 1.
Right. So now this says x equal to y squared minus 1.
Mm-hmm.
I want to say x equal to what? So I
Yeah,
want to make that same comparison.
you
So
want
in
to
order for
make
me,
x, okay, x
yep,
equal to that
right. So in order for me to do that, I multiply both sides.
by the
Right.
number. I see,
Uh-huh.
I see. I get it.
So
Thank
that,
you.
yep, not a problem. So now we see that I have x equal to negative y squared plus 1. And so we know that that's not the same as the original equation. The original equation was y, positive y squared minus 1. And so our statement here, since this is not the original equation, the function is not symmetric with respect to the y-axis. All right, make sure we go to that because that's what we're going to do for the next two as well. I'm going to plug in the negative variable. The next one we'll plug in negative y and see what we get when we simplify. I want to know, is it symmetric to the x-axis? So we'll substitute in negative y for y. So we plug in negative y in, notice that's negative y squared. And we know the effects, we talked about that already, the effects that a negative, that a square will have on a negative. We know negative times a negative. Didn't mean to write it like that, but that'll give you a positive 1. Write that better. So negative times a negative will give you a positive. So that will be positive y squared now. And so the statement here, since this function is the same as the original, it is symmetric with respect to the x-axis. All right, any questions on that? All right, so the last one, talking about being symmetric to the origin. This time you have to substitute negative x in for x, negative y in for y. And that's what I do right here. So that's negative x equal to negative y squared minus 1. And then I have that situation again where I have negative x sitting here. So I multiply both sides by negative 1. And that's x equal to negative y squared plus 1. And we have that statement again. Since this function is not the original function, it is not symmetric with respect to the origin. So you have to simplify it. Once you simplify and reduce, make a comparison to the original equation. If it is the original equation, it is symmetric to with respect to whether it be the y-axis, x-axis, or origin, whichever one you're testing. Once you simplify, if it's the original equation, it is symmetric to that axis or origin, or if not, then it's not. It's not symmetric to it. All right. Questions? Any questions? We have one more thing I want to discuss because it's very similar to this, and since we've done this, we got a few minutes left. We can knock that out, but it's very similar. And it's talking about even functions and odd functions. Anybody still copying this top part? All right. So when you talk about even function, if you plug in negative x and it is the same as the original function, then it's considered even. For an odd function, if you plug in negative x and each one of your signs are opposite the original function, then it is considered odd. So once again, when you plug in negative x, once you simplify, if each one of your, well, I'll say it like this, if you have the original function, then it's an even function. But then for an odd function, when you plug in the negative x and you simplify, each one of the signs are opposite, then it is an odd function. All right. So the directions for this type of exercise, it would say determine whether it is even, odd, or neither. All right, so for the first one, we have f of x is equal to x cubed minus 6x. So you plug in negative x wherever you see x. And so over here, just re-emphasizing the idea of when you have an even power versus an odd power. If it's even, your negatives are going to cancel and give you a positive result. If it's odd, your negatives, all your negatives will cancel except for one and just leave you with that negative. And so, in other words, if I have negative 1 to the 400th power, the result is going to be positive 1. But if I have negative 1 to the 505th power, the result will be negative 1 because there will still be a negative left over because it's odd. So when I look at negative x cubed, the result is going to be negative x cubed. And then here, negative 6 times negative x will be positive 6x. So once you simplify, you compare that expression to the original. And since each sign is opposite the original function, it is an odd function. All right. Next one, g of x is equal to x to the 4th minus 2x squared. Going to follow the same procedure, substituting in negative x, but this time we have an even power on both of our negative x's. So that would be x to the 4th, that would be a positive x to the 4th minus 2x squared. And this function is the same as the original, so that means it is even. Then the last one. We have h of x is equal to x squared plus 2x plus 1. Oh, somebody trying to, I want the chat open up. Okay, there we go. The negative cancel first right here because of your square. So negative times negative is positive. So this negative never touches that negative. It doesn't get a chance to. Yep. Somebody asked me why that negative didn't get there and turn to a positive. So that's what we were talking about. All right. So for the next one, h of x, we're doing h of negative x. So we plug in negative x into each. So this turns positive. This stays negative. So that's a positive x squared minus 2x plus 1. And if you compare it to the original, all signs are not the same because you know we have the negative 2x there. And neither are all signs opposite. So that means it is neither. So remember, it has to be one or the other. Either it has to be all the same or all opposite in order for it to be even or odd. So this one is neither. All right. Questions.
Do you have time after class?
Yeah, I got a few minutes for my next one. Yep.
Yeah, because this entire part, I didn't get it. Like, why are you putting, I don't know, like the negative x, I don't know where you're getting that from. The negative, it's like, it's,
Now you're talking about this negative x?
yeah, that negative x.
That's a part of the test. That's just the process.
So you just put it in there, it doesn't matter.
Right. Yeah. If you're trying to test whether your function is even or odd or neither,
You got to put a negative x.
Exactly.
Every time you have to solve it, you put a negative x. And then can you scroll up just a little bit to the second problem? I just have another question. In here, when it's negative 2 times negative x and square, when you say negative times negative, you squared that. Why didn't that square disappear from there when it's like negative 2x squared? It's still there.
Right. So this is negative x
Times
times negative x. So
which
now negative times negative is positive.
Positive.
But then you got positive x times positive x, which is x squared.
Oh, okay, I see.
Yeah. So really the only thing that simplified was the fact that we had a negative in there, but we don't have a number to plug in for x to make the square to go completely away. So it still would just be x times x.
I see. So every time there's an x or a x, you just plug in negative x and solve from there.
Yep. And so, so when you talk about testing for even, odd, or neither, or even going back to when we're testing for symmetry, you're always those are the tests that they give you. So there's no other way to do it. That's just the process.
That's just the process.
Yep. That's the way you would test for it.
Okay, I just need the last problem, just part C. I see. Oops.
Any other questions before we close out? Real quick, not going away from it, but this is where we're at next class. Oh, I didn't mean to hit that button. All right, there we go. Right here, difference quotient. That's the last part of 2.2. So don't let me forget, guys. 2.2 difference quotient is where we want to start next class. So we'll finish out 2.2 on next class. So if you're good, I'm good. I will see you guys on Monday. Have a great weekend. Be safe. If you need something else from me, feel free to stay back and ask away. Outside of that, have a great weekend.
Again?
For chapter 1, it'll be due on the 15th, midnight.
Okay.
All right.
I have a question.
Yep.
I did the test already. Do I have to send you my work? Because I kept that just in case I needed to send you the.
Yes. So for each test, whenever you submit your test, I need to see that scratch work. But for your homework, you're good to go just for your test.
Okay, so do I just email that to you?
Yes, that'll be great.
Okay.
Plus,
Yes, sir.
are we We having class Monday? It's President's Day.
As far as I don't know if college even celebrate President's
I already
Day.
know. That's why I asked. I saw it on my calendar.
Yeah, I'll check it out. If not, I'll shoot you guys an email.
Okay.
Yep. Thanks for asking that. Yep. All right. Anybody else before
So
we?
for the, just real quick,
Yeah.
yeah, this symmetry one is kind of confusing. Do you get a lot of students who get confused about it, or am I
Oh
the
yeah.
only?
Yeah. It's not a big a deal.
So the function is when it's like, when you're trying to solve it, let's just, let me give you an equation, okay?
Hmm.
Let me see. Let's say h of x equals x to the third plus 2x plus 5. Everywhere there's an x, you just plug in negative x.
Now, which one are you trying to test for symmetry, or are you trying to test for even or odd?
No, I'm talking about even, odd, or neither.
Yeah, right. So right, you would plug in
And
negative x.
anywhere there's an x, you just plug in negative x, and then you go on and solve from there, right?
Yep.
And then for the symmetry part, let me see. You substitute. Wait, that's the same thing, right? For the
It's the
symmetry.
same. It's the same thought process, but you are testing for different ones. So if you're testing for symmetry with respect to the y-axis, then you'll be. Let's say if I'm just going to use something simple.
Mm-hmm.
Then I would plug in negative x here to see if I get the same thing.
Yeah.
If I'm
And if I'm
testing
for
for symmetry for the x-axis, then I'll plug in negative y
yeah,
and leave the x the same. And so, yeah. And then
and then
symmetry
solve
for
from there with the -1, like -1 on the outside, multiply both sides by -1, and see what the solution ends up being.
Mm-hmm.
Yeah.
Yep.
All right. Thank you, Professor Tucker.
All right, not a problem. And if you have any more issues, just bring another example or one that you may have had an issue with. If you bring that to class, we'll walk through. It's not a big deal.
Okay. All right.
He ain't alone.
Thank you, sir.
He's not alone.
Oh, yeah, it's not. Yeah, I know that. Most of the time, when you have questions, that's why I encourage people to ask the questions in class, because very rarely are you sitting on the island.
Yeah, this one was kind of confusing when we were going through symmetry.
Mm-hmm.
Because there were multiple parts to. I got the increasing, the decreasing, the constant. That was easy, but when you got to relative extreme, no, that was easy too. Defining symmetry, that's where it started getting confusing, where you're like, substitute negative x for x, and x for negative y for y, and all that other stuff.
Yep. So yeah, I understand. That's fine. If, like I said, when you're trying the stuff out and you can't figure out why they got to where they got as far as the answer is concerned, yeah, just either shoot it to me in the email. Mr. Coley will let you know. He's good for that one.
Okay.
Shoot it to me in email or bring it to class, and we'll knock it out.
Okay.
I got one quick question.
Yes, sir.
That 5 is times 1x negative, right?
You talking about right here?
Yes.
Yeah. So that when you simplify that, that would be y equal to negative 5x plus 7.
Yeah. So that's not in.
Right.
How would you write that solution? It's
So now
not,
this one, we were looking at symmetry with respect to the y-axis.
yeah.
So that would not be symmetric to the y-axis.
Yeah, that is not.
Mm-hmm. Right, because it would have to be the exact same thing as your original equation.
Okay, I killed some brain cells on this one.
You're welcome, sir.
Thanks for adding more gray hair. I appreciate it.
Thank you, Professor Tucker.
Not a problem.
Have a good weekend, guys.
Yeah, you're the same.
You too, man. See you later, Professor Tucker.
Take care, sir. All right. Anybody else? Everybody
I
good?
have a question.
All right.
Okay, this one seems kind of slight, but this is the only one on like the homeworks that I'm really not getting.
Okay.
It's on like 1.5. It says to complete the square of x squared minus 7x, add blank, like an integer or simplified fraction. I don't know what I'm like not doing.
Okay. Yeah, not a problem. So you always take this middle term right here, and you're going to take half of that and then square it. And so half of that would just be -7/2, since it doesn't simplify all the way down. It just be, I mean, you know, evenly. 2 doesn't divide into it evenly. You can just leave it at 7/2. And then we're going to square it. That'll be 49/4. So what you should be adding to that is 49/4. And then if I'm not mistaken, they're going to ask you to write it factored. So this factorization is going to be x. And if you're not comfortable with how it looks, because it may look a little funky as far as factoring is concerned, whatever half your b term was is what goes here. Yeah. And that's it.
Okay. Thank you.
Not a problem, because that one didn't ask you to actually solve it, right? They just wanted those steps part of the process.
Yeah.
Yeah.
Okay. Perfect.
All right. Not a problem. You have a good one.
You too.
All right. Anybody else before we close? All right. You guys have a good one.